Okay, so we'll just be a little more to the side. So, as I said, just a final point, which is slightly closer to the course. This is substituting in on how do we model knowledge in distributed systems. So essentially, you think of a particular protocol in a particular setting as generating a large number of runs. Okay, all the runs that are possible runs of the protocol. Now, at any given point in a given run, every process has a local state. Okay, in the simplex complex view, this would be the history it had up to that point. But in our case, your local state is just what information you have locally. So you could have deleted your mailbox, everything up to last month. We used to do that a few years back. And then you wouldn't know what messages you got last year, but you would know what you got last week. So essentially, we say that at a given point, a process I knows some fact phi if at all points where it has the same local state. So this is run 1 and run 2 and run 3, whatever. You have lots of runs here. And when we ask in a particular run, R2 here at time t, whether I knows phi, then it knows phi if at all points where it has the same local state, it can't tell them apart from the current point. So remember, as a muddy child, if I couldn't tell apart the situation where I was dirty from the one where I was muddy, I didn't know if I was muddy. And after round k-1 went by, and none of you other dirty children said you were dirty, then I could separate, at time k-1, I didn't know whether I was muddy, and at time k, well, all the things that were possible, as far as I'm concerned, were only situations where I was muddy. So let's look at the acute depictions of this, acute depiction, and let's assume that n is 3 when we're going to describe a world, the initial state of the world as a triple x1, x2, x3. We have 3 children with xi is 0 if I is clean, xi is 1 if I is dirty. And child 1 distinguishes 2 worlds if, initially, if the values of x2 and x3 are not the same in the one world and in the other. I can't tell my own whether my value is 0 or 1, but I can tell, so my local state is actually what I see, which is the foreheads of the 2 other children. So, well, no longer we have a better view, but we have to stand next to it. So this is essentially the situation initially. Okay, this is the situation where nobody's dirty. Here, number 3 is dirty, but 1 and 2 are clean. Here, number 3 is dirty, 2 is dirty, and 1 is clean. And notice that child number 2 can't tell this node apart from that node, because 1 and 3, what he can see is the same in this world. So I'm number 2. Here I'm dirty, and the one to my right is clean, and to my left is dirty. And here I'm clean, and the one to my right is clean, and to my left is dirty. So these 2 points are indistinguishable by 2, although the others distinguish between the 2. And you can notice that we get a very nice cube form describing the initial situation. Now, so here, of course, nobody knows there's a muddy child. And similarly, well, I guess in these nodes, well, everyone, all the 2 that are not muddy know that there is one that's muddy. Okay, these 3 nodes are nodes with 1 muddy child. But not everyone knows that there's a muddy child here, because child number 1 thinks he could be clean. Okay, you can't tell this apart from that. So in these points, we have 1 muddy child. Not everyone knows there's a muddy child. In these points, this point here, here, and here, we have 2 muddy children, and you can see that here everybody knows there's a muddy child, because whether you go by the one possibility for player 2, there's a muddy child at this node, and in the other place that he considers possible, there's a muddy child here, and in the one that 1 considers the alternative possibility, and similarly here. Okay, so we have 2 muddy children here. Everybody knows there's a muddy child. And from this node here, in all possibilities, everybody knows. So each one of us knows that everybody knows there's a muddy child, and therefore here with 3 muddy children, we have everybody knows that everybody knows there's a muddy child. Okay? In general, I know that you know something if for all things that are possible by me, in both cases, in this case it's just 2, and the 2 possibilities possible by me, you know this fact. So then that would mean that in everything that's possible by you, which here is this and this, and here is this and this fact holds. So here I know, 1 knows that 2 knows that 3 is muddy, because however you go by 1, 2 knows that 3 is muddy because he's muddy. He knows he's muddy here, and he knows he's muddy here. So 1 knows that 2 knows that 3 is muddy. Common knowledge, a fact, is common knowledge if it's true in the whole connected component of the particular node we're looking at. Okay? And being not being common knowledge means basically being disconnected in the sense of this graph from, not being common knowledge means being connected to a point. Phi is not common knowledge if there's a path to a point where phi does not hold. Okay? So common knowledge is connectivity dimension 0 a la Maurice. Okay? That's the connection to what it should be. Okay, so what happens here? So this is time 0 after 1 round. Well, not after 1 round. Once the father speaks, he says, there's at least 1 muddy child. It becomes common knowledge that this is impossible. Okay? So after that, if we ask what initial states are possible, essentially, this becomes disconnected. Nobody considers the situation where everyone started clean as possible. And even here, I mean, the father said one of the children is muddy, and so this became disconnected. And now, in these cases, the muddy child knows that he's muddy, because you see there's, for the red guy, the only possibility is this node. For the blue guy, the only possibility is this node. The other alternative has been cut off. Okay, we're disconnected from it, and therefore here these guys know that they're muddy. So if in fact k is 1, then the answer of the muddy children becomes yes. And after the first round of no answers, then, well, it becomes common knowledge that we didn't have 1. So all of these become disconnected. This is still connected. These in these three situations, we have that the muddy children know that they're muddy. Only if, in fact, all three are muddy, is it the case that none of them knows that he's muddy. And then, after the third round, well, we're here. If we survived 3 rounds to the third questioning, we're here. We all know there's no alternative. I know that the other 2 are muddy, but I have to be muddy as well. Okay, so that's the picture. And basically, this is a taste of what the model of knowledge looks like when we use it. Okay, so now I'm going to talk about an application of knowledge to analyzing coordination in distributed systems, and mainly for analyzing the role of time bounds in synchronous systems. And this is joint work with Ido Ben-Zvi, a student of mine. And it starts out from Lamport's happened before relation. So probably the most cited paper in distributed computing is a paper by Leslie Lamport called Time, Clocks, and the Ordering of Events in Distributed Systems from 1978. And this is defined. That's interesting. Okay, so there he defined a precedence relation between events in an asynchronous system where basically, oh, something's really wrong here. This is strange. Okay. E arrow L E prime basically says that E happened before E prime according to Lamport. According to Lamport is because we're going to have something later. And pictorially, basically, it means E happened before E prime in an asynchronous system if there is a message chain starting at or after E and arriving at or before E prime. Okay, so we would say that this event happened before that event. Locally, you can compare the timing of events by the sequence at the local site. A send of a message always happens before the receive. Okay, you can't receive my message before I sent it. And if we close, if we take these 2 rules and close transitively, then we get the partial order, which is called the Lamport precedence or the happened before relation. So here E happens before E prime, E double prime happens before E prime, but E would not be said to happen before E prime here, even though if this is the time axis, then in fact E may have happened at time t and E double prime at time t plus 4, but there's an equivalent. It turns out that if we're looking at an asynchronous system, then you can construct another run in which the local histories will have exactly the same sequence of events. We don't have a clock, we don't have a notion of time. So you can actually pull E double prime here. Look at the run where E double prime actually happens at t minus 1. The history of P2 would be exactly the same as it is in this run. And in fact, E would not happen before E double prime if E double prime were here. Everyone would live the same life, would have exactly the same experiences in life because they don't have a clock, don't have a watch, they don't know what time it is, and still, and the alternative run, E double prime does not happen before E. Okay, so I hope. So the formal definition of happens before is E precedes E prime, happens before E prime. It's the minimal binary relation where if E occurs at process I at time t, E prime at process I at time t prime, and t comes before t prime, then we say that E happens before E prime. If E is a send and E prime is the matching receive, then we'll say that E precedes E prime. I'll move to another file in a second. And for transitivity, we just close transitively. So you take the smallest transitive relation with these properties is the happened before relation. Okay, we have so okay, so this is fundamental to asynchronous systems, and what we're going to talk about today is how do clocks and bounds affect causality and coordination. So this really, in some sense, it captures all the information we have about the ordering of events in an asynchronous system, because there are equivalent runs. If E does not precede E prime in the Lamport sense, then nobody can ever tell whether E actually preceded E prime or not. And the question is, what happens when the world is synchronous? So we have a global clock, and we're assuming, so there is a global clock, everyone has access to this clock, or clocks are perfectly synchronized if you like, and we have a network where every channel has a particular bound on how long it takes messages to travel along this channel. Okay? No failures in this talk. And this is a model that's been studied. Leslie Lamport looked at it in '84. And we're going to study coordination here by looking at a particular coordination problem that we call ordered response, where we have some triggering event which is spontaneous. This could be, typically this is an external input. So the bank gets a deposit or a request for withdrawal, or there's an indication from the smoke detector in room 403, or whatever happens to the system that the protocol didn't design, didn't plan. Okay, this is a spontaneous event that needs to be responded to. And so the order response problem starts from defining a particular trigger event and a sequence of required responses, where every response is just an action, a particular action that needs to be performed by a particular process. And what we require, we say a protocol solves ordered response for a particular trigger event and a sequence of responses if it guarantees that whenever, in every execution where the trigger happens, each of the responses occurs, and they occur in sequence. So A1 occurs not before A2, and A2 not before A3, and so on. And these actions are performed only in response to ET. So just to simplify the analysis, if ET doesn't occur, then none of these responses happens. Okay, well, that's the general coordination problem. We'll look at a particular instance to get a feeling for it and for how it can be solved in a synchronous setting. So we're looking at a network with Charlie, Bob, Alice, and also ran Susan. The story is that Bob is a banker. Charlie has an account in Bob's bank, but his account is frozen because of bad credit. Now Alice has a check that Charlie has given her, and she'd like to cash it. But if she presents it to the bank before his account is active, she's going to be fined rather than getting her money. So they actually need to coordinate their actions. We're looking at what they need to do is we're looking at a trigger event, which is Charlie depositing a sufficient sum to reactivate his account. This is spontaneous because Charlie can't be trusted, right? He's already in trouble, and he's waiting until his aunt will give him money to get his act together. So this is the triggering event of the ordered response. If this happens, then after this happens, Bob should reactivate his account. Okay, if he reactivates before he deposits, Bob could be in trouble. Shouldn't happen before. And once the account is active, Alice can cash the check. She's really eager to cash her check. So this is an instance of an ordered response problem. The trigger is if Charlie deposits, which we can only pray, hope that will happen, spontaneous event. After this event, this should be the first response, and after it, Alice performs the second response. Okay, if we're in an asynchronous system, we can prove that in fact the only way to do this is if there's a message chain starting from Charlie's deposit, passing through Bob's reactivation, and getting to Alice. Okay, if there's without the message chain, doesn't have to be a direct message from Charlie to Bob, from Bob to Alice. It could pass through, say, Susan, but there has to be a message chain starting from Charlie after he deposits and getting to Alice before she can cash her check in the asynchronous world. But with clocks, things are different. Well, first of all, you might say, okay, have Charlie deposit on Sunday, Bob reactivate on Monday, and Alice on Tuesday. They don't need to coordinate anything. Okay, this is a good plan, except that we're assuming it doesn't work because Charlie, this event is a spontaneous event. We don't know when Charlie is actually going to bring his deposit to the bank. He's unreliable. So only once this happens can the others happen. So since his deposit is spontaneous, there needs to be information flow from the deposit to Bob and from Bob's reactivation to Alice. Okay? And the question is, obviously we can still do the same act as we did in the asynchronous world, but with synchrony we can do better. Okay, so let's look at an example, particular situation. So suppose at time t, Charlie deposits. Now suppose that in this example at t plus 2, Bob receives an indication. He gets a message saying deposit happened. And Alice at, say, t plus 4, I guess this might be. And we assume that the bound on the channel from Charlie's deposit to Bob has the bound is 10. Okay, so it's guaranteed, and the bounds and the network are assumed to be common knowledge initially. They're given to the programmer. So it's guaranteed that by time 10, t plus 10, if the deposit happens at t, by time t plus 10, Bob would receive indication and reactivate. I assume that reactivation and caching all take 0 time for simplicity. Okay, so here Alice receives notification of Charlie's deposit, and if she would go to cash her check, everything would be okay here. Okay, she can go cash her check, except she doesn't know that she can do that. Okay, a protocol that would have her go and cash her check here would be dangerous, because if the message along this channel would take longer, then she would be fined and not get the money. Okay, so essentially, when she gets a notification that there was a deposit at time t, she knows that by t plus 10, this will happen. So without any communication between Bob and Alice, she can, at time t plus 10, go and cash the check. Okay, in the asynchronous world, she would have to have a message chain, a Lamport causal chain starting from Bob, reaching her before she could go and cash the check. So there would have to be concrete indication that Bob reactivated. But here, she can say, okay, Charlie deposited at time t, this I know. I'll wait until t plus 10, go to the bank and cash the check. There doesn't even have to be a channel between Bob and Alice for this kind of coordination to be possible.
Charlie has to send Alice time t?
What? In this example, he sent to Alice at time t and to Bob at time t.
No, he has to send the time.
Yeah. We assume here, for this talk, think of messages as containing all the information that may be relevant here. Okay, so yeah, messages contain the time in all my examples for simplicity. Not in the theorems, but in the examples. Okay, so this example showed us that you can actually coordinate and order events without Lamport causality when using your information about timeouts. And again, the essential point, if we go back to the previous slide at the overall intention of this talk, only at t plus 10 does Alice here know that Bob is reactivated. He actually reactivated at any time between, say, t plus 1 and t plus 10. At t plus 10, she knows that he has. Okay, in this particular execution, it happened t plus 2, but she didn't know that that's where we were. Okay, another example is Susan enters the picture. Susan is Bob's supervisor. Okay, Bob is a banker, Susan is supervisor, and Charlie's deposit sends a message to Bob, to Susan. She gets it at t plus 3. Alice gets it like the other day at t plus 4. So at this point, Alice knows that at t plus 10, she can cash her check. Okay? Because of the same reasoning, the argument we gave just in the previous slide. Now suppose that at t plus 7, she receives a message from Susan informing her of this deposit. So she got, at t plus 4, she got one from Charlie. But the message from Susan at t plus 7 also says that Susan sent a message to Bob. If the bound between Susan and Bob is 4, then Alice can know that by now Bob will have definitely received indication of the deposit. In fact, he received it before. But as far as Alice is concerned, she knows at t plus 7 that Bob is guaranteed to have heard about the deposit, and so she can update her plans and she can run to the bank at t plus 7 and cash her check. Okay, she gets... So what happened here was that we're not just using information, a priori information about the transmission bounds, but we're also using, we can update this information based on communicated messages that we receive along the way. Does that make sense? Okay. So, well, another point I'll go over quickly. When we have message bound, we have bounds on message transmission, then we can also time out on messages. So if we know that a message from me to you takes 5 time steps at most, and I don't send you a message at time t plus 5, you can see that I haven't sent it. So we can consider that to be a null message. We can think of my not sending you a message at time t is the same as my sending you a null message at time t, which you receive at t plus 5. At t plus 5, you know I haven't sent you a message at time t. And this could be a signal. For example, that I'm ready with the escape car, in front of the bank. or whatever. It's a message I don't really want to send explicitly, I can send implicitly. If there would be a problem, I would call you to coordinate dinner. But if I don't call you by time t, if I don't send a message by time t, you should know that I'm ready, in front of the branch to take the money before Alice can cash a check. So you can actually send the message send a null message when there are global clocks and time bounds. And this example shows that we can use Alice. If Alice were sending, if Susan was sending a message, there's no indication from Charlie, there's no indication from Charlie, as long as there was no indication from Charlie. And then at time t plus 3, she does receive one, so she no longer sends Alice a message saying there's no indication from Charlie. Then at t plus 3 plus the timeout, which in this case is 5 time units, Alice knows that there was an indication from Charlie, that Bob is guaranteed to have received the message sent at t plus 3 from Alice by t plus 7, so she can actually cash the check here. Okay, so these are different ways of solving ordered response in the synchronous world. And I'm going to formalize this and mention a couple of theorems and then relate this to knowledge, all in 3 minutes. Well, not in 3 minutes, but okay. So, well, essentially, this I'll go over quickly. We don't really need, we generalize Lamport causality slightly by allowing information to flow through null messages, through timeouts. Okay? So we define a happens before relation, if you like, or a synchronous causality relation between pairs process I at time t and process j at t prime, where we have the same locality condition we had before. I at time t can causally affect I at later time t prime. If there's a send here and a receive here, then there's a causal relation. If no message is sent by I at time t, then I at time t can causally affect. There can be information flow by this null message from I at time t to j at t plus the bound between I and j, and we can close transitively. So this is actually the black part is Lamport causality, and we can extend that by saying, well, a null message is also a type of a message. This is the small part of the story. Okay, well, we can prove that if you have an ordered response of just a single response, if something happens, then a particular response needs to be performed, then there has to be a syncausal connection between the trigger and the response. Okay? And this could involve messages being sent, and basically it says there has to be a generalized message chain which consists of messages and timeouts between to pass the information to the responder that the trigger has happened. This is the simple case. Okay, we write a syncausal message chain as a squiggly arrow like this, and in fact, every response has to have, okay, let's see. There has to be a syncausal chain between the trigger and each one of the responses. Now, a new binary relation we define between pairs of processes in time to mean that there's a guarantee that a message sent by I at time t to j is guaranteed to reach j by time t prime. So we say that there's a timing guarantee between it and jt prime if t prime is at least as large as t plus the distance between I and j in the weighted graph, the graph that's weighted by the transmission time. So essentially, this was our network with upper bounds on message transmission. Then we can ask, what are the shortest distances between, say, x and u? In this graph, well, the shortest distance here is 9. And in fact, if we send a message through z from x to u, then we can guarantee that information from x will reach u in 9 time units. Okay? So essentially, we say that there's a timing guarantee between it and jt prime if there's enough time to be guaranteed, that I sending a message to j at time t is guaranteed that j would receive it by time t prime. Okay, if he sends it in the best possible way. Now, if we look at, so we had the ordered response problem of Alice, Bob, and Charlie. And in fact, what we have is a combination of syncausality and timing guarantees that plays a role here. In the first day, we had a syncausal chain, a message from Charlie to Alice, which arrived here. There's a syncausal chain between Charlie at time t and Alice at t plus 10, and a time bound between Charlie at time t and Bob at t plus 10. Okay, you remember that in fact the message may have arrived earlier, but this structure allowed Alice to respond at this point. The second and third days, in fact, we had a slightly different picture. We had a syncausal chain from Charlie through Susan to Alice, and a bound guarantee between t plus 3 and t plus 7, allowing between the time between this node here along this syncausal chain and the time at which Alice responds. Okay, so essentially the information from this node ensured Alice that she knows this message would arrive by this time. So the information from Charlie was guaranteed to arrive by time t prime. In fact, what we can show, I'll skip these, is that all of the ways in which we can coordinate two responses are different flavors of the same structure, where there's a syncausal chain from Charlie from the trigger to the second response, and some node along the path. It could be this node in the original case, but it could be other nodes in other cases, from which there's a timing guarantee, guaranteeing, in fact, to this node that this has already happened. Okay, the combination is, this is an actual generalized message chain, a chain of messages at timeouts, and this is information that we don't have explicit indication about. We're guaranteed to have happened based on the time bounds. Now, more generally, so this is the picture if we have two responses. And what we can show is that if you have three responses, then every execution of ordered response with three responses, there would be a syncausal chain from the trigger to the third response, and two nodes along the way that have to have timing guarantees to the time of the third response, to the first responder and the second responder. In general, we define a structure that we call a centipede, which looks like this. Okay, there's a syncausal chain from the trigger to a response, and there are nodes along this chain from which there are timing guarantees going to the other responders in order. And what we can prove is that every protocol that solves ordered response with a trigger and k responses has to satisfy the property that in every run where the trigger actually happens, there has to be such a centipede form. So what this really means is that whereas in the asynchronous world, every execution of ordered response would have to have a message chain going from the trigger to the first responder, the second responder, all the way to the last one, this centipede is the generalization of a message chain in the synchronous system. This is a way of capturing the interaction between communication, which happens along the syncausal chain, and time bounds, and the way they combine in order to allow coordination in synchronous settings. So, as I said, centipede generalizes message chains. I'll go for 4 more slides. One generalization you can consider is instead of ordered response, since we have a global clock, to consider a situation where we want all the responses to happen at the same time. Okay, like coordinated attack. You know, we have to announce the fact, the merger between the companies in Tokyo, New York, and Tel Aviv the announcements have to happen at the same time. And maybe as soon as possible, but still at the same time. Well, what we can prove is that for every solution to simultaneous response, this version of coordination, what we have is there has to be some node with a syncausal chain from the trigger to this node, and timing guarantees from this node to, so Susan, gets a message, she sends it to Bob and Alice, and there's a guarantee that her message would reach both of them by t+8, then they can perform their actions simultaneously at t+8. This we call a centibroom because of the form. And, well, we can prove this theorem. And both of these results basically come from, both of these theorems come from a reduction to a knowledge-based analysis. In a protocol for ordered response, if the trigger happens, then when the third responder performs the response, he has to know that the other two have happened, okay, are now or have happened before. And so 3 has to know that 2 knows that 1 knows about the trigger, okay? And we can prove that, in fact, to get this kind of nested knowledge, you need a centipede. Okay, this we need a few lessons to show. But basically, we reduce solving ordered response to obtaining nested knowledge. And we prove that nested knowledge about a spontaneous event can happen only if you have such form. And in fact, this is tight in the sense that in the full information protocol, like the protocols that Morris was talking about, where you send all of your information to everyone, and suppose you do that in every round, then this is in fact tight. So this is necessary and sufficient for knowledge gain of this type and for ordered response. And if we have a simultaneous response, then when we perform our simultaneous responses, we have common knowledge we're doing that. I know that, I'm performing this action because we're all doing each our own response right now. So in order to do this, it has to be common knowledge we're doing this. It has to be common knowledge that a response has happened. And we can use the previous theorem in order to show that obtaining common knowledge that an event occurred requires this form of coordination. So basically, a knowledge-based analysis, non-trivial and subtle, gives us a way of capturing coordination and the role that the time bounds play in coordination in synchronous systems. And I think this is, well, there are lots of open questions around this. Semi-synchronous and then various variations, shared memory, whatnot. But basically, what this work shows, well, it presents ordered response as a natural coordination task and a way of studying coordination in a system which combines, well, both the need for information flow, knowing about a trigger that has happened, but also information that's needed in order to coordinate and ordered responses. And as we saw, this is not the same because we can use information about communication to coordinate sometimes without explicit communication or even implicit communication. And we have a generalization of Lamport's happened before using causality. We have timing guarantees, and we combine them in the notion of centipedes, which are necessary for every solution in order response. This has nothing to do with how you want to solve it. If you solved it, then you've constructed centipedes. If you've solved it simultaneously, you must construct centibrooms. And this is another application of knowledge-based analysis. And again, if in the course, this will be later in the course, but that's an example of how we apply the theory. Questions?
I guess the obvious question is, instead of, so you look at order where everything has to happen simultaneously, and you turn it sideways to have it happen simultaneously. But imagine you have a partial order.
If instead of a sequence, you specify a partial order.
Yeah, yeah. Is there a something as simple as the centipede?
Well, it's not as simple. You can combine centipedes in a subtle way, but yeah, there is an answer. It's not as clean to draw, but yeah, we've handled that. But say semi-synchronous, even assuming clocks are not synchronized, even if clocks do move at the same rate, at the rate of real time, but they're not synchronized, the story becomes quite a bit more subtle there. I mean, we can still prove that you have to have a centipede, but centipede isn't, you might need more than that. Because I know that there's enough time for you to have received it and for her to have received it before you. But I don't know what your information about her clock is. And so you might be compensating because you think there might be a big difference between, you know that he did it at time t on his clock. What do I know about your information about the time? I can know that all clocks are actually synchronized, and still I'll have to think my information about what the previous responder's knowledge about the clocks comes into play, which it doesn't here. Here we're, but so there's much more to be done that's open here. Questions? This was a bit quick, but it'll be more leisurely next semester for going once, going twice. No questions? Okay. Thank you.